In this module, we will continue with our discussion on the quantum mechanical treatment of the linear harmonic oscillator. We have already studied that linear harmonic oscillator is a basic model for a vibrating diatomic molecule. We call it linear because vibrations are assumed to take place in one direction, that is x. So, in the earlier module, we have already seen how we wrote the Schrodinger equation for a linear harmonic oscillator. We found out that the potential energy is equal to half kx square because for simple harmonic motion, we showed that using classical treatment and with the help of Hooke's law, one gets potential energy equal to half kx square. Then we wrote the Schrodinger equation, and then our purpose was to solve this Schrodinger equation to get vibrational energy and the wave function. We have already got the expression for the vibrational energy through the solution of the Schrodinger equation. While solving Schrodinger equation, we first reduced it into an appropriate form by making certain substitutions, and we converted this equation into the form which is d2 psi v by dy square minus y square psi v is equal to minus lambda psi v. Then this equation is the equation which can be easily factorized. We used two operators, one is creation operator and other is annihilation operator. In annihilation operator and creation operators, making use of these two operators, we solved the Schrodinger equation. And through the solution of the Schrodinger equation, we got the expression for the vibrational energy, which comes out to be equal to h nu multiplied by v plus half, where v is the vibrational quantum number and nu is the frequency. We also showed that the vibrational quantum number can have values starting from 0, 1, 2, 3 onwards. And when v has the value 0, we get the lowest vibrational energy, that is half h nu, which is called the 0 point energy. So all these things we have already discussed. Today we will go a step ahead, and that is we will find out what are the corresponding vibrational wave functions for the linear harmonic oscillator. The wave function is of the form psi v is equal to nv a plus cap psi 0. Now the first question is how to find psi 0. That means the wave function for the lowest vibrational state. We have already seen in our earlier module that the annihilator operator expression, and that was that a cap, which is the annihilation operator, when it operates on psi v lambda minimum, this gives you 0. We have seen it already. Now suppose that psi v lambda minimum is psi 0, because we cannot have a wave function for lower value than this. Therefore, a cap psi 0 becomes equal to 0. Now a cap you know is d by dy plus y, and therefore if we simplify it and further integrate it, as you can see here, it's very simple. We find that psi 0, the ground state vibrational wave function, comes out to be e raised to the power minus y square by 2, and in a general form we can write it psi 0 is equal to n0, which is the normalization constant, multiplied by 1 multiplied by e to the power minus y square by 2. So this is what we have got as the lowest wave function, psi 0. Let's now try it and solve for psi 1. Again in this case, psi 1 will be equal to n1 then a plus cap psi 0. Now A plus cap is creation operator. Therefore, if we put it for psi 1, it will become n1 A plus cap n0 e to the power minus y square by 2. And then if we simplify it further, we get psi 1 is equal to n1 n0 then d by dy minus y e to the power minus y square by 2. And now if n0 and n1 are combined, it becomes n1 prime, and therefore if we further simplify it, we get that psi 1 is equal to n1 prime 2y e to the power minus y square by 2. So this is the expression for the first, that means first excited state you can say, which is for v is equal to 1, that is psi 1 is equal to n1 prime 2y e to the power minus y square by 2. If you remember, what was the expression for psi 0? For psi 0 we had psi 0 is equal to n0 into 1 e to the power minus y square by 2. So in this way we have been able to get these two wave functions. Extending our discussion further, we can similarly find out psi 2. As you can see here, psi 2 is written and it is calculated exactly in a similar manner, and here we define the new normalization constant, which is n2 prime, that will be equal to n2 n1 n0, and if we simplify it, ultimately we get psi 2 is equal to n2 prime, then in parenthesis we have 4y square minus 2, then e to the power minus y square by 2. So from these expressions for the wave function, one can say that the general form of the linear harmonic oscillator wave function is psi v is equal to nv hvy e to the power minus y square by 2. Here hvy, they are the various Hermite polynomials. If you remember, in psi 0 its value was 1. That means when v is 0, its value is 1. When in the case of psi 1, as you noticed earlier, it came out to be 2y, and for v is equal to 2, its value came out to be 4y square minus 2. So these are the general expressions, and this is how one can write the wave functions. Only thing which one needs to keep it in mind is how to calculate the normalization constant, that is NV. For calculating the normalization constant, we will use the normalization equation condition, and that is psi Vx dx should be equal to 1, and this integral is within the limits minus infinity to plus infinity, because these define the corresponding boundary conditions. And if we solve this integral and make the appropriate substitutions which we had made earlier, so ultimately using the standard integral, one can see that NV, that means the general expression for the normalization constant, comes out to be 1 upon alpha 2 to the power v factorial under root pi and then whole square root. This is a general expression. Here, as you can see, alpha is equal to h cross upon m omega under root. So in this way, we have been able to find out the wave functions for the linear harmonic oscillator and their general expressions. Now these results which we have obtained for a linear harmonic oscillator, these can be extended to diatomic molecules. Because if you remember, we said at the very beginning that linear harmonic oscillator is a basic model for a diatomic molecule. Only difference would be that in the case of a diatomic molecule, we will replace mass by the corresponding reduced mass. That means the frequency of vibration for a diatomic molecule will be given by 1 upon 2 pi kf upon mu under root, where mu is the reduced mass and is equal to m1 m2 upon m1 plus m2. With all this background, now we have noticed that for a linear harmonic oscillator, the energy is given by the relation EV is equal to V plus half h nu. And we have also seen that the total wave function psi v is given by nv hvy e to the power minus y square by 2 and define the different terms. Now, in a harmonic oscillator, if you look at the energy expression, you will notice that as one goes from V is equal to 0 to 1 to 2, the energy levels are equally spaced and the spacing is equal to h nu. That means equal to h upon 2 pi kf upon mu under root. That means the spacing between the energy levels in the case of a diatomic molecule, because we have used a reduced mass, will depend upon the force constant as well as reduced mass. H upon 2 pi is of course constant. Therefore, you can notice that as the value of the force constant will increase or as the reduced mass will decrease, the space levels will become more far away from each other. That means spacing between them will increase. But at the same time, as we have already mentioned, in the ground state, energy will always be equal to half h nu, and that is what we call as the 0 point energy for a diatomic molecule. We have also shown a diagram where you can see the plots of the harmonic oscillator normalized wave functions and the corresponding probability densities. Wave functions are shown on the left hand side, whereas the corresponding probability densities, which are the square of those wave functions, those are shown on the right hand side. So they are very well, you can see that in the case of left hand side, wave function is also negative and positive, but probability densities are always positive, therefore they are always lying above and they are not less than 0. These are the things which you must notice. So these plots are for the various energy states. First, if we start from the bottom, the lowest plot is for ground state, then the next is for 3 by 2 h nu, and so on. It would be interesting to discuss at this stage the symmetry of the vibrational wave functions. A wave function will be odd if we replace x by minus x and it becomes negative of that. But if it remains unchanged, then it will be even. Now, if we look at our wave functions for a linear harmonic oscillator, the expression is psi v is equal to nv hvy e to the power minus y square by 2. Now there are three terms in this. Now let's look at this one by one. Now the exponential function e to the power minus y square by 2 is an even function of y. So because it is y square, so even if you replace y with minus y, it will remain unchanged. On the other hand, Hermite functions are even for even value of v and odd for odd values of v. You remembered that if we had v is equal to 1, the corresponding Hermite polynomial was 2y. Now 2y is odd. But if we had v is equal to 2, the corresponding Hermite polynomial was 4y square minus 2. That is again an even one. So Hermite functions are even for even value of v and odd for odd values of v. Therefore, what does it mean? It means that for a harmonic oscillator, psi v state will be even or odd depending upon the values of v. For even values of v, vibrational wave functions will be even. while for odd values of V, vibrational wave functions will be odd. This is very, very important. If at any stage we have to multiply two wave functions, you have to remember that odd multiplied by odd will give you even, and even multiplied by even will also give you even. But if you multiply even with odd, it will give you odd. So these are also very, very important results which are often used in calculations. And also you should remember that if in an integral the entire integrand is odd, and if the limits are from minus infinity to plus infinity, then the values of that integral will be equal to 0. These things are very helpful in many of the calculations. Lastly, we will discuss about Virial theorem. This is a very important theorem in quantum mechanics. It basically applies to the systems having potential energy. According to this theorem, if potential energy can be expressed by the expression V is equal to Ax to the power B, where A and B are constants, then the kinetic energy is related to the potential energy in the following manner. That means 2 times the kinetic energy will be equal to B times the potential energy. Now in the case of harmonic oscillator, if you remember, we showed that potential energy is given by half kf x square. So B is here too, and therefore if we apply Virial theorem, 2 times kinetic energy should be equal to 2 times potential energy. That means kinetic energy should be equal to potential energy, and that would mean that each one of them should be equal to half of the corresponding vibrational energy. This is a very, very important theorem. This you can verify yourself using all those what we have discussed and find out whether this Virial theorem applies for the linear harmonic oscillator or not. For example, you can apply it to the ground state. You know that for the ground state, total energy is half h nu, that means 0 point energy. Therefore, if Virial theorem is to be true, then kinetic energy should be equal to potential energy should be equal to 1 by 4 h nu. And this we can show by finding out separately potential energy as well as kinetic energy. For finding out potential energy, you will use the expression integral minus infinity to plus infinity psi 0x, that means you are talking about the 0th state, half kf x square psi 0x dx. If we substitute the value of the 0th wave function and then substitute all other values and solve this integral, you will find that its value will come out to be 1 by 4 h nu. So in this module today, we have extended our discussion on the quantum mechanical treatment of the linear harmonic oscillator. In the last module, we calculated the expression for the energy of a linear harmonic oscillator, and we showed that this energy comes out to be EV is equal to h nu V plus half, where V is the vibrational quantum number and nu is the frequency. We also said that V can have values starting from 0 onwards, 1, 2, 3, like that. In this module today, we calculated the values of the wave functions. We found out that the general expression for the vibrational wave function comes out to be psi v is equal to nv hv y e to the power minus y square by 2, where nv is called the normalization constant, and it is given by the expression nv is equal to 1 upon alpha 2 to the power v factorial under root pi and then whole square root. Here alpha is equal to h cross upon m omega under root. And the corresponding Hermite polynomial, the general expression for them is hvy is equal to minus 1 to the power v e to the power y square, then in parenthesis dv by dyv e to the power y square. We also showed that when v is 0, Hermite polynomial is 1. When v is 1, Hermite polynomial is 2y. and when v is 2, Harmonic polynomial is 4y square minus 2. So we also discussed about the symmetry of the vibrational wave functions, and we showed that the vibrational wave function is even for even values of v and odd for odd values of v. We also gave the plots of the normalized wave functions as well as the plots of the corresponding probability densities. All these results are very important and provide a model for a vibrating diatomic molecule.